There is, in fact, reason to worry that it might not be. Hiring more teachers, after all, costs money. So wealthier school districts can better afford smaller classes. But students at wealthier schools also have other advantages over their poorer neighbors, including better facilities, newer books, and better paid teachers. Moreover, students at wealthier schools tend themselves to come from more affluent families and thus have other advantages not directly associated with their school. For example, California has a large immigrant community. These immigrants tend to be poorer than the overall population, and in many cases, their children are not native English speakers. It thus might be that our negative estimated relationship between test scores and the student-teacher ratio is a consequence of large classes being found in conjunction with many other factors that are in fact the real reason for the lower test scores. These other factors, or omitted variables, could mean that ordinary least squares analysis done so far has little value to interpret to the superintendent. Indeed, it could be misleading. Changing the student-teacher ratio alone would not change these other factors that determine a child's performance at school. To address this problem, we need a method that will allow us to isolate the effect on test scores of changing the student-teacher ratio, holding these other factors constant. That method is multiple regression analysis, the topic of chapters 6 and 7. Summary. Number 1, hypothesis testing for regression coefficients is analogous to hypothesis testing for the population mean. Use the t-statistic to calculate the p-values and either accept or reject the null hypothesis, like a confidence interval for the population mean. A 95% confidence interval for a regression coefficient is computed as the estimator plus or minus 1.96 standard errors. 2. Number 2 of the summary, when big X is binary, the regression model can be used to estimate and test hypotheses about the difference between the population means of the big X equals 0 group and the big X equals 1 group. Summary 3. In general, the error U sub I is heteroscedastic. That is, the variance of U sub I at a given value of big X sub I. Var of big U sub I given big X sub I equals X depends on X. A special case is when the error is homoscedastic. That is, when variance of big U sub I given big X sub I equals X is constant. Homoscedasticity, only standard errors, do not produce valid statistical inferences when the errors are heteroscedastic, but heteroscedasticity, robust standard errors do.